Okay, so the last step in all of this is to generate the actual molecular formula. So to do that, you have to be given some sort of mass of the compound itself. It would be some sort of experimentally determined, we found it to have this sort of mass before you could get to your molecular formula. So you'll notice I set everything up. And one thing I did, and I didn't start over because I think it's a good opportunity to talk about magic math. I did our percent composition that it was given, 54.9. I turned it into 54.9 grams, just treating this whole thing as 100 grams. And I went ahead and did my moles to get everything into moles of carbon, hydrogen, and oxygen. And then I get my mole numbers. And I was getting tired of doing this today, so I started to do magic math, which was just divide this by 2.27, divide that, and just have like this stream of consciousness for math. Problem is all of this does not equal 9.13 divided by 2.27. You can't do that. In your scratch work, if you want to do it, that's fine, so long as you're paying attention to what you're doing. 9.13. That got messy. But for something that you're going to turn in, you would be losing points for magic math. Whatever you put on one side of the equation must equal what's on the other side. If it doesn't, it's voodoo. You can't do it. So I did all those steps, and my smallest one was the 2.27 moles. So this became 1 mole of oxygen. The 9.13 became 4 moles of hydrogen, and that became 2 moles of carbon. So this is my empirical formula. Now we want to turn it into a molecular formula. Well, we're given that the compound weighs 44 atomic mass units. Well, don't forget, these numbers here, when we first started talking about the periodic table, also represent atomic mass units. So we can look at them as grams per mole, we can look at them as atomic mass units of this atom, of that atom, and so forth. So what we want to do is determine how much does this empirical formula come out to. So it would be just simply the 2 times 12.011 grams plus 4 times the 1.008. Let's do AMU. Sorry about that. Plus the 15.999 AMU times 1. Let's see what that comes out to. And we add it all up and we get 44.053 AMU. And considering the molecular mass that we were told should be 44 AMU, I would divide the molecular mass, the 44 AMU, divided by my empirical mass. I know, it's 1, but I just want to show you. And we see that's darn near 1. What that tells me is that this empirical formula is also the molecular formula. If it were higher than that, formula, let's see, 2H4O. Say that came out to 2, then we would go back and multiply our subscripts by 2. So we'd pretend that that's a 1, so this would become 4, 8, and 2. And if it were a 3, it would be the same thing. It would be 6, 12, and 3. That's the exact way that we would determine the difference between HO, which is actually written OH, I know it doesn't seem like it should matter, and H2O2. These two things, at the end, I would get an answer of 2, and I would multiply it through and get the actual molecular formula. That's how it's done.